Now for ideal gases, we have to re-express our formulations of Gibbs equations. Recall for an ideal gas, our change of internal energy, du, is equal to our constant volume specific heat times our change of temperature. And on a per mass basis, our pressure is expressed as our gas constant R times our temperature per our specific volume. If we substitute these expressions into the first formulation in Gibbs equations, we'd have TdS is equal to du plus P d nu, which is equal to Cv naught dt plus RT per nu d nu. And if we divide by temperature, we can say our change of specific entropy, ds, is equal to Cv naught dt per T plus R d nu per nu. If we integrate, assuming our constant volume specific heat is a function of temperature, we'd have ds is equal to integral from state 1 to state 2 of Cv naught dt per T plus R times the natural log of nu2 per nu1. And note we'd have to integrate Cv naught divided by temperature with respect to temperature. Now, as Cv naught is a constant, we can pull this outside our integral, and ds would be equal to Cv naught times the natural log of T2 per T1 plus R times the natural log of nu2 per nu1. And this is very helpful if we have our temperatures and our specific volumes at our initial and final states. However, we can construct a similar expression in terms of our constant pressure specific heat. To do such, we recall that our change of enthalpy for an ideal gas is Cp naught dt, and on a per mass basis, our specific volume, nu, is RT per P. If we substitute these expressions in to Gibbs' second equation, which is T ds is equal to dH minus nu dP, we'd have TdS is equal to Cp naught dt minus RT per P dP. Now if we divide by T, we'd have our change of our specific entropy, ds is equal to Cp naught dt per T minus R dP per P. If we integrate and assume Cp naught is a function of T, we'd have ds is equal to the integral from state 1 to state 2 of Cp naught per T dt minus R times the natural log of P2 per P1. And thus we'd have to divide Cp naught by T and then integrate it with respect to T. Now, if Cp naught is a constant, this expression becomes ds is equal to Cp naught times the natural log of T2 per T1 minus R times the natural log of P2 per P1. And this expression is useful if we have our temperatures and pressures at our initial and final states. Now, to avoid the integration of Cp naught, where we could use table A6, we can define standard entropy, which allows us to use tabulated values for our change of entropy. And this is done by setting our entropy at 0 Kelvin to 0 kilojoule per kg at 1 atmosphere. And thus we define our standard entropy, S naught, as a function T, as an integral from 0 to T of Cp naught times the natural log of T2 per T1. Now note the 0 superscript. This indicates that this is standard entropy. Now this is very useful because a change of our entropy, ds, which was S2 minus S1, we can now evaluate our standard entropy at T2 and our standard entropy at T1, replace our integral. That is, our standard entropy at T2 less our standard entropy at T1 would be equal to integral from state 1 to state 2 of Cp naught per T dt. And that's the term within the parentheses on the right-hand side of our ds equation. The remainder of our Gibbs second equation is minus R times the natural log of P2 per P1. And this is useful for our standard entropy values, which are merely a function of temperature, are tabulated in table A7.1 for air and A8 for other ideal gases. Now let us see how this works. Say we want to determine the change of our specific entropy of air, which goes in a process from 300 Kelvin in 1 bar to 1000 Kelvin in 3 bar. And we're going to assume that Cv naught or Cp naught are constant, and then we are going to use standard entropy. For us to begin, we'll first assume that Cp naught is constant. Since we have our temperatures and pressures at our initial and final states, we're going to use the second formulation of Gibbs equations for ideal gas. That is, ds is equal to Cp naught times the natural log of T2 per T1 minus R times the natural log of P2 per P1. If we substitute in values, this is 1.004 times the natural log of 1000 Kelvin per 300 Kelvin minus 0.287 kilojoule per kgk times the natural log of 3 bar per 1 bar. Thus, our change of entropy is 0.893 kilojoule per kgk. Now, if we use our standard entropy, we have to look at table A7.1 and recognize that our equation becomes ds is equal to our standard entropy evaluated at T2 less our standard entropy evaluated at T1 minus R times the natural log of P2 per P1. Thus, we have 8.13493 minus 6.86926 kilojoule per kgk less 0.287 kilojoule per kgk times the natural log of 3 bar per 1 bar. and we have a value of 0.950 kilojoule per kg/K. This is more accurate, for our constant pressure specific heat varies as a function of temperature, and thus our standard entropy accounts for this variation of Cp with T, as opposed to treating it as a constant.